Hello, everyone. Good morning. I hope you had a great weekend. Let's wait like 5 minutes for the other students to join. Today's lecture will be quite easy. Like it will be a very short lecture, and it will be the final lecture for, let's say, traditional computer vision. Starting the next lecture, we will start speaking about deep learning and computer vision. And this will be also the only lecture or the last lecture included in your midterm. So the next lecture will not be part of your midterm, right? In the meanwhile, while we're waiting for friends, does anybody have any questions, maybe any remarks regarding the final project? Maybe some concerns about the homeworks, they're too difficult, maybe too easy, something like that.
I have a question, maybe if it is possible.
Yeah, of course, go ahead.
Is it possible to make the project just like an implementation for a paper, or it should be like something really new and with some new work? I mean,
if the paper does not have an implementation already somewhere on GitHub, then that's definitely a new contribution. That's definitely something new, right? If you publish it, then that would be good.
Okay, but it is not necessary to be like a new contribution.
Yeah, of course. Yeah.
Thank you.
You're welcome. Of course, any new contributions will be regarded as a higher achievement and certainly will get better grade and easier grading. But we're not asking the students to basically do separate research for our course, right? So not unless you're working already on something that's related to computer vision and it's like research that's already published and you can share with us, then there's no need to create something new.
Perfect. Thank you very much.
You're welcome. How about the first homework? Was it easy?
Yeah, actually, we want to discuss first homework because it was kind of easy, but it took a lot of time in terms of fine-tuning parameters and
nice.
Applying some filters, and we collected some statistics from our groups, how much time did it take, so we could share it with you.
So how much time on average did it take?
So for the first group, it was like 25% of people spent from 6 to 8 hours, and there are about 30% of people who spent about more than 10 hours on this. So it's it was not difficult, but time consuming, and we are asking, was it proportional to the amount of points that it costs? So we spent about 6, 8, 10 hours, but its race is 5 points, so it's kind of strange. Maybe it was planned that we will complete it faster, but it wasn't for us.
I see. So from what you're saying is the programming of the task was quite easy, but the changing of the hyperparameters took too much time.
Yes, and applying some filters, applying some dilation, other morphological operation, just experimenting with it. It took very much time, and because of the requirement of the interfaces and documentation, so it is okay to require this, but it took this time because of it too.
Of course, certainly.
I believe.
Well, I will definitely speak with Karam about this, and I will check his point of view. From what I think, probably there was some sort of an easier way to do the fine tuning. From his point of view, of course, like I wouldn't assume that he would ask you to spend more than 10 hours on a homework. That's definitely a bit too much. Or is it? I think for me personally, a homework should take less than 1 hour, much less. But yeah, I'm going to certainly discuss this with Karam, and hopefully this will not be the problem of the next two homeworks, especially since we decided to make the first homework kind of too hard and the next two homeworks too easy, since they will be in the same time with your group project, right? So probably that was the reason why Karam made this homework a bit too difficult or too long, mainly so that the other homeworks would benefit from this difference. But thanks a lot. Thank you for pointing that out. Anyone else has any questions? Maybe about the project guidelines?
Yes, actually, what kind of difficulty you expect from us of our projects?
That's a good question. So the difficulty level should be like discussed basically with with Karam. So he basically should define the difficulty of every project. So you submit what your project proposal is, and he would tell you what the difficulty of that project is. And depending on the difficulty of your project, our grading would be either like more relaxed or more strict. So if you're going to do something very hard, we're going to be very easy with you. Even if you don't make it and if you fail, you're still going to get like a very good grade. But if you're going to do something very easy, then we're going to be like very strict with the coding, very strict with the documentation and stuff like that.
Okay, got it.
Yeah,
Thanks.
so basically the harder is your task, the overall, the better should your grade be.
Also, the guidelines say that we should do it in pairs. Is it okay to do it alone?
Certainly, yes, but you should just ask Karam right before just to confirm that there are enough spots, right? So because he wants a certain number of projects overall, so it would be nice to confirm with him before starting your own.
Well, technically there is a group of 3 people, so I guess.
Yeah, exactly. Yeah. That's what I said. Yeah. So
Okay.
Basically, if he manages to make the groups of 3 with the groups of 1, then it should not affect him that much.
Okay, thank you.
That's nice. You're welcome. Thank you. Now, let's start our beautiful lecture. Let me share the screen. Yeah. So just like quickly, we will go back to the last lecture, just to speak again about the SIF detector and the SIF descriptor. And then from there, we will start our new lecture. Well, we'll start the new lecture, or the final lecture on computer vision, basic computer vision. Yeah. So the goal of this last lecture was to basically do a good feature extraction that would allow us to identify some points of interest in the image. These points should be able to kind of describe the main characteristics of this image. And then from these points, basically each one of these points will have its own description. And from there, we can do stuff like feature matching. We can do stuff like, you know, this panorama stitching. Another like very good example was like lately we had like a program where the background of one of the people was like kind of ad was not accepted by the people running the show. So I think what would be interesting would be to take like the background of the person and try to regenerate the video without that background. So that's definitely something that we could do using this feature matching and feature description. Another very cool application, especially for robotics people, is this visual SLAM, where you just walk around a new area and you construct its 3D map. And basically using that 3D map, you will be able to understand where you are in the future. In our feature descriptors, we spoke about two main feature descriptors. The first one is the Harris corner detector and SIFT. So Harris corner detector works, aims at, of course, detecting corners. That's what its name suggests. And it does that by detecting the areas with the highest change. Of course, this computation of the highest change was a bit too difficult. So we tried to estimate it or simplify it using the, using the Tyler series expansion. And from there, we basically represented it as a ellipse equation and constructed our Hessian matrix. And this H matrix, we just calculate its eigenvalues. Of course, the eigenvectors don't matter that much, but the eigenvalues are very important. And from these eigenvalues, yeah, this is just like a recap about eigenvalues. I'm sure Karan already did like a very good lab about this. Yeah. So after we have our eigenvalues, we construct our, well, basically this, right? So in our eigenvalues, we have lambda 2 much bigger than lambda 1, or the opposite side. This means this is an edge. If both of them are very large and kind of similar to each other, that means this area or this place is kind of a, how do you say this? Well, a corner. And of course, if both of them are very small, then this is a flat region. Somebody took the liberty of building this awful formula or this function, which kind of combines both the lambdas in a manner that kind of simplifies the this detection, right? And this way, we have the R being very positive or large, very positive, very large positive number for corners, and basically something close to 0 or something negative for everything else that doesn't matter to us. We can see from here the examples, how does the R of every point look like? And then this is how we do non-maximum suppression to basically remove all of the excess areas. Finally, the next lecture, we will speak about non-maximal suppression in more detail, right? Yeah. So of course, there is like a better way of doing this. Instead of belonging to the window or not belonging to the window, now we belong to the window, but with a certain probability. So just with a certain weight. These weights are automatically generated from a Gaussian distribution. So this is just the summary of overall the Harris corner detector. And we said that the Harris corner response, or the R, is quite rotation invariant. So the eigenvalues don't change. This means for the same person, for the same area, right? For the same point. So only the eigenvectors are changing. The eigenvalues don't change, meaning the R should not be different. Also, the R is not dependent on the value itself, but dependent on the change in the intensities or the change in the values. So it should be, so it should be invariant to intensity changes. So something from like night to dark, from night to day should not really influence the R that much. One problem with, of course, Harris corner detector or the R is that it's very scale variant, right? So basically the scale does affect it very much. And this is because in this window, when we have a corner, if we zoom in too much, then the same size of the window would give you, as you can see, only edges. So this is one potential problem with the Harris corner detector. And somebody was like, that awful, horrible formula is just a bit an exaggeration, and said that it would be better if we just take the response as the minimum of the two. So basically, if one of them is large, one of them is small, then the minimum should be small. If both of them are large, then the minimum should be large. And this is all that we are looking for. Now for the scale invariant feature transform, it's very similar to what is it called? To what the Harris corner detector is doing, but instead of working with something that is very scale variant, now we're working with something hopefully scale invariant, right? It has two main parts, so basically the detector part and the descriptor part. So let's start with the detector part. The idea here was to basically build a window size depending on every single point of interest, right? So for example, here, we keep on increasing the size of the window until a certain criteria arrives. And of course, in here, we took the best size from the start, for example. Now, how did this happen? Of course, we simply try to find a function, basically like this, and find its local maximum, right? So, for example, for a small region size, this function is not optimal. And for a very large region size, this function is not optimal. So of course, this is a good function, and these are bad functions because they have multiple local maximums. And this is just like a very large region of local maximum areas. Of course, such function does not exist directly, or it's very hard to calculate. So the simple trick that they found was, let's just describe it pretty simply. They decided to make a pyramid with lots of variations of the same image, right? So for example, this is the first corner, this is the second, third, and fourth. Like imagine that this is like double the size and this is like double the size of this one. And at every single size, we're going to blur out the image with multiple sigmas, right? So, you know, the sigma does influence the content of the values. So, for example, this pixel with a small sigma would only contain its neighborhood, its direct neighbors' values. But with a very large sigma, it would be the combination of a very much larger area. And then what we do is simply go back to this function. Sorry. We go back to this function and calculate, let's say, for example, this is size 1, this was size 2, size 3, size 4, size 5, size 6, size 7, size 8. For each one of these, we map them into their function values and we take their local maximum. And we take the local maximum over the different scales and the different octaves. Nice. Now, once we have that, we would have like a bit lesser pixels than what we started with, but however, we still have like thousands of pictures. Oh, sorry, thousands of points. So similarly to what was done in the Harris corner detector, we're going to use a Taylor series expansion to basically evaluate or simplify the evaluation of every single one of these different points. And certainly we're going to use a threshold. So if the R is smaller than a certain threshold, that's not something that interests us, right? So we're trying to aim for as much of corners as possible and trying to stay away from these edges, because corners usually tend to contain a bit more information and be more representative overall of the object overall. So similarly to what we used in the Harris corner detector, we're going to use a Haitian matrix. From that, we use its eigenvalues. If one eigenvalue is larger than the other, then we know this is an edge. So we use a ratio. If the ratio is greater than a threshold, then that point is discarded. After that, what we simply do is we take the points that interest us. Now they're much fewer points. We go to their neighborhood. We describe it using a process very similar to HOG, right? So we've seen this. We take the orientation of the gradients and their amplitude, put them on a histogram like this one, and then we take only those who are above 80% of the maximum value, and that would be the combination of the orientation vector of that specific point. Now that we finished with the point, what's it called? Sorry. Yeah, feature or the point detector. Now let's go speak about the point descriptor, right? For the description process, still all of them are very similar to what we have seen in the first lectures with HOG, right? So what it does is basically compute the descriptor of the local image region about each key point. So we have a 16 by 16 window like this one. Each one is like 4 by 4. And we have in each one, we have 8 bins, which are predetermined bins of directions. And we just put the direction, we just like put the values of the directions based on the amplitudes of each bin. So SIFT is a pretty robust algorithm, kind of, and it can handle changes in viewpoint for up to 60 degrees. This was like determined empirically, and can handle significant changes in illumination, and it is fast and efficient. These are like a few other algorithms to do detection of points and description of these interest points. And then we saw that feature matching is basically just combining the list of the features in here with the list of the features in here based on.
Could
Yes?
I ask the question of the previous slide?
Yep.
No. The one about feature matching. You said that we use L2 distance, but it should be not absolute value, but squared. No, but on this slide we have not squared, like further. Yeah, here.
Yeah, this. You see when somebody does this, they don't put the square in general, right? So this is called the norm, right? So it's not this absolute value, you see?
Okay.
This is absolute value. This is the norm. The norm is a function which is like the sum of the square root over the sum of the values squared, right? So this is the norm this is the L2 norm at least. Okay, sometimes you see the 2 in here, sometimes you see a 1, sometimes you see infinity in here, right? It depends.
Yes, it was kind of confusing because there is no number.
There we go. So this is like the typical norm you would have of, this is a feature vector, and this is a feature vector. So it's not like 5 minus 3, right? So this is the norm of a vector minus a vector. Okay, but very nice question, right? So this is definitely the L2 norm that you're already familiar with, right? This the square root over the sum squared. Nice. So again, we said that since you might have too many similarities, instead of just matching directly with the closest one, we match with the one which has the best ratio of closest to second closest. And then this is what the feature matching allows you to do. It kind of allows you to do many things such as object detection and feature matching, of course. How do we measure the evaluation of this thing? Again, similarly to what you would for any classification project, either ROC, area under the curve, either, what is it called, the other guy? Yeah, F1 squared, F1 score, accuracy, you name it, right? Thank you so much. And that's it for the last lecture. Does anybody have any questions? This was like just a quick revision. Hopefully, like majority of you already knew everything I was saying so far. And just for info, there is no quiz for today, right? So there is just the small lectures, right? For this new lecture, we're going to speak about a bag of visual words, which is just a very simple technique that was like kind of taken from natural language processing, or kind of like, let's say, inspired from it, right? So we'll speak about the origins of bag of words in natural language processing, and then we just try to make its implementation for images. You'll see that it's very, very logical explanation. Once you understand bag of words for normal words, you would be able to kind of understand the rest pretty easily. So this is just like a small recap for image classification. Given a set of positive training images like this, so this is for motorcycles, and of course, negative training images like this that don't, try to classify a test image as to whether it contains the object or not, right? So this is the aim of image classification. We usually have, like, for image classification, we're working with this weakly supervised learning setting, meaning we only know if the image or if the object is inside the image or not. We don't know if it's a segmentation, or what is the segmentation of the object itself, or what is like the pixels that belong to the object and the pixels that don't, right? We just know that some of the pixels in here belong to the class of interest. So usually there are like 3 stages. The first one is to represent each training image using a vector. Second one is to train basically a classifier to discriminate over these vectors. And then we apply the trained classifier to test on test images and evaluate its accuracy. Bag of visual words. So the first one is the texture, right? Once we understand what texture, why texture is pretty important, we will understand how bag of visual words work. So texture depicts these spatially repeating patterns. Just so we would be able to understand this easier, just take a look at these images, right? So just looking at this one, you don't see the bottle of yogurt, but easily from this pattern that you're looking at, like milky pattern, you can understand that this is directly like a yogurt pattern, right? For example, this one, these are rocks. Very easily, you can see that there is like a certain pattern repeating in these rocks. And for those who work with like design and stuff, you always see, you know, those websites that give you different patterns and textures to put on your like background of your website and stuff. And same thing for radish, same thing for human face, same thing for many of these concepts. There's always some repeating pattern that comes again and again, and this is like the texture of that object. So for example, here we can see that texture is usually characterized by the repetition of a set of basic elements or textons, right? It's the identity of the textons, not their spatial arrangement, that matters. For us, a face looks like this, right? There we go. Texture really doesn't care about how the eyes are related to each other, how the nose is related to the eyes and stuff like that. It only cares about the existence of these concepts together. Let's put the, right, yeah. As long as they are in the same image, that means this is a face for like texture-based classifiers. Of course, this is a problem and a good thing in different places, right? So let's just go back here a little bit. And for example, for this image or this type of wall, you can easily see that there is like a set of repeating patterns that are always there, which is just the square, this triangle like looking down, and the triangle or the Y looking up. Same thing for this one, same thing for this one. You can always find their repeating patterns. after finding these textons, right? So these smaller repeating elements or repeating patterns, you could do something similar to, let's say, hog, but instead of having the gradients, the direction here, or the gradients, yeah, the direction of the gradients here with their amplitude, now you have just the texton, and how much present is that texton, right? So how many times is it being repeated? So the origin of the second motivation, let's say, of a bag of visual words is the bag of words itself for words, right? So we take a document like this, and we're trying to classify whether this document is, let's say, a scientific document, or is it something like more about religion, or something more about sports, right? So what we simply do is we take a large text and we split it to words. Right, so we have its words. Now, every single word would come here to this kind of histogram. So here we see, for example, this one contains a lot of speech about robot, shimp, I have no idea what this is, SMU and stuff. And here we're speaking also about robots, but we're speaking more about soft, ankle, sensor, view, and stuff like that, right? So this kind of gives us an idea about what the content of the document is. This is a very important, let's say, thing. For example, here we have this was a good movie. This is good, right? So basically, if we put the histogram of these features or these words, we would have the word good in here. And if we send it for a classifier, the classifier would see that the person mentioned the word good, and we classify this one as a good or positive review. Now, one very major problem that you would notice is if we said this was not a good movie. So basically it will add just one not in here. Why is this bad, right? So for example, if it was this simple, then the model would look, it would see that there is word not here, would associate kind of not as a bad thing. But what if the sentence was much longer and the model would not know whether this not was speaking about not good, meaning it's a bad movie, or it was a good movie and the author used not in a different area, not related to basically saying bad words about the movie. So this is what happens when you remove the spatial relationships between the words, and this will be the same problem that would happen later on with bag of visual words, right? So again, this is a good thing and a bad representation at the same time. So for example, if I give you these smaller parts of an object, can somebody tell me what this object is, right? Just from its spatial, well, its different textons, right? Is this a horse?
Looks like motorcycle.
Nice, yeah. So it looks like a motorcycle. Like a horrible person would say it looks like a car, might be true, but it's certainly not a horse, certainly not a tree, and definitely not a person, right? So only using these textons, we were pretty much able to shrink the area of the different objects that it might belong to, and definitely it's very clear that this belongs to a motorcycle. So this is the effectiveness of this representation. So as we have said, this certainly belongs to a motorcycle. So as you can see, this is the collection of local features or the bag of features that we're using for this object, which is the motorcycle. Can somebody tell me how could we, like one of you, just like randomly say, I have an image and I want to represent it in the same manner, right? In this vector form, where each one of these values is some sort of a texton or corresponding to a certain texton, and this is like how many times this pattern was repeated. Let's say 3 times, 2 times, 20 times, right? Can somebody tell me how would you do that? How would you find what are the important textons in an object? Based on what you have already seen, of course.
The most repeating one.
The what?
The most repeating one, like if they repeat a lot in the same object, this means they are.
Let's go with a 4i in range of image if I exists in image, we do it twice, right? So basically we are calculating every pixel.
And not pixel, but a window of pixels.
Okay, so we take a window of pixels
Yeah.
and we compare it to every single other part of the image and we count, right?
Yes.
Certainly that's a very good idea and definitely works very well. Anybody has maybe like a simpler idea that's a bit faster, right? It's not going to be too much faster, but a bit faster.
I can also use the interest point from the previous topic.
Oh, that's nice. That's nice. Yeah, go ahead. Which one
So-
exactly should we use?
We take, for example, like if there is a window that has a lot of interest points, we can take it, use it.
Which one of the previous algorithms should we use, right? So we studied Harris. Let's say
Like
we studied
Harris could work.
Sift
Also,
also could work.
Sift would be for size invariant. So
Yeah,
scale
sure.
invariant.
So basically any of the previous algorithms work very well. So what we could do is we find points of interest in the image like this. And then we describe them. And there you go. You have some text on of the image. Now for the repeating part, we will see how we can handle this a bit later on. But you're going in the correct direction. So one of the most important concepts in computer vision models is this bag of visual word models. So this is something that I would highly disagree on. Bag of visual word models are completely not being used anymore. But it's a very, very interesting idea, to be honest. So it's used to build some accurate systems. For image classification, it actually gives like somewhere around like high 90s, which is very, very interesting, right? Some like even neural networks, they need some sort of heavy training to basically reach this level, or some sort of content-based image retrieval and many other systems. So this is what bag of visual words look like. What we would do is we take an object, or take a set of objects later on. So we take an object, find the parts that are interesting, and basically put them in a bag. So you can say why we use this concept of a bag. Certainly, we don't want to have an order between these things, right? There is no spatial order or any information or configuration between these objects. They're just laying there in the image. So this is why we use the terminology of a bag. Saying, for example, that we want to build a sort of a classifier, right? So for faces, we have these. For example, this is a face. This is what vehicle. What is this? Cycle. How do we call this?
Bicycle.
Bicycle. Thank you. So we have a bicycle and we have this violin in here. So if we like extract all of their bag of visual words and combine them together in this kind of a dictionary, let's say, and then from there, we would build a distribution for each one of them. So for example, for the face part, we're definitely not going to find a car seat in here. We're not going to find a violin bass. We are going to find an eye, and maybe this is like a nose or something like that. Say similarly for a bicycle, we're going to find bicycle parts, but we're not going to find patterns very similar to a human eye or patterns very similar to a base of a violin. Same thing would go for the violin, right? So if we give this feature vector to a classifier, and this one, they would easily be able to kind of build some sort of, non-linear classifier around these distributions. And there you go, you have a very good image classification task. So the pipeline overall would be like this. Extract what are the interesting features, cluster features to form the visual vocabulary. This is kind of an interesting idea, and I would like you guys to understand or like tell me why would we use it and kind of bring it up to, well, you guys would propose it directly because it's pretty easy, very logical idea. Quantize the features using the visual vocabulary and then represent the images using the frequencies of their visual words or the vocabulary that we generated from this codebook generation process. Feature extraction, right? Pretty simple. This one, we extracted these features. This one, we extracted these features. This one, we extracted these features. The second part would be to learn, again, this visual vocabulary or this codebook. Third step would be to quantize the features using a visual vocabulary. What does this quantization mean? It means basically we, let's say we put them in a 2D space, right? So it was part of an image, so it's a matrix of pixels. We try to put it in a 3D or 2D space of vector like this. We're quantizing it. And then we represent each image by the frequencies of these visual words. How do we extract the features? Again, any algorithm that you guys would like. Even, for example, a random algorithm that just takes every 10th pixel, like this. Let's say something like this. Even something like this might work pretty well. But of course, if you use something a bit more complicated, such as a Harris corner detector or SIP detector, definitely it's going to give you much better words. Now, we extracted these feature vectors from each image in our dataset, and now we need to construct our vocabulary of possible visual words. Now let's imagine the scenario. Sorry. Let's go back and imagine it here, much better, right? Yeah. So let's imagine the scenario. We have face number 1, eyes, nose, and stuff, and we extract the features from it. It gave us the eye, gave us the second eye, gave us this one, and gave us the face. Now we give it another face. This is face number 2. What will it extract? Same things: eye, nose, mouth. Third face: eyes, nose, mouth. Now, after like you build, let's say you have built a very large vocabulary with each one of these different patterns, you would end up finding that the majority of them are quite repetitive and they're very similar to each other. How would you be able to basically keep only the ones that are interesting to you, right? Or the ones that are not pretty much repeating it themselves? Simply what you would do is you would try to extract features from each one of these and then represent it in some sort of a vector and then you calculate basically the distance from each one of these vectors. If, let's say, if the distance between this one and its closest neighbor is too big, then we keep it. If the distance is too small, then we delete one of them, right? So this is one way of doing things. Can somebody tell me a different way, right? Say we have points like this. So now we're no longer working with images or parts of images. Let's imagine we are working with points. So this is what we just described, right? We said that there will always be a lot of patterns very similar to each other, creating these different groups like this.
We can find the centroids of each group.
Oh, that's very nice. That's a very good idea. So, right, like we could try to do something similar to what we have been describing before, which is non-maximum suppression, right? So we take all of this neighborhood and keep only one of them, right? So this is one way. But an easier way to do it would be, as your friend suggested, basically finding the centroids of each one of these. Or any other clustering algorithm that would group these guys together, and we basically remove all of them and keep only one. Which one should we take? As your friend suggested, if you're using k-means, you could take the one in the middle or like the center of this cluster, or if you're using dbScan or something else, you just take something that is like inside this cluster. Like, for example, anything that is any one of these points would work and do the job correctly. Nice. So again, in this codebook generation part, we're going to use a classifier or a k-means algorithm to create these cluster centers. Why are we using these cluster centers? Simply to remove the repeating patterns that we find in similar images of the same object. Say we are working with trying to detect a person. So the face is definitely going to repeat multiple times in every single picture, meaning we're going to have many extracted features which are very similar to each other. So in order to remove this huge repetition, we use a k-means clustering algorithm. Now, what is very good about k-means is that k is human defined, right? So you define and you control how many features will you extract or how many features will you be using for the creation of your codebook generation, right? Or your vocabulary. Sorry. Let me just close this. Nice. Hopefully not too disturbing. Nice. So now that we have our codebook generation part, the rest is pretty simple, right? So this is how the vocabulary construction is done. We take our different features, we put them in this space. Of course, it could be a 3D space, 2D space, or n-dimensional space, depending on what the feature descriptor you're using. And then we just group these using k-means algorithm. So it's going to look something like this. So this is what k-means would look like in the end. And then we take the centroid of this one, the centroid of this one, and the centroid of this one to represent each group. There we go. So this is our visual vocabulary. For a bit more detail, this is what k-means is. I'm sure that everyone in you has already seen what k-means like multiple times. So first, you select initial centroids at random, or using k-means ++. And then you assign each object to the center, which is the closest to it, to the cluster with the nearest centroid. and then compute or update the centroid as the mean of its assigned objects. Repeat this step 1 and 2 until convergence. Usually convergence is either there is no change or like a certain number of iterations have passed. So let's take, for example, a look at a practical example of what k-means would look like. So imagine that we have 5 objects, let's say 5 people, and this is their height and width. And we're trying to, let's say, classify adults versus kids, right? So these are person 1 is 167 height in centimeters, person 2 is 120, 113, 175, and the last one is 108. So let's say into 2 clusters of adults and kids, right? We simply build this one, some random cluster 1, some random cluster 2, and then we compute the Euclidean distance between each point and its the 2 different centroids. So for example, here we see centroid 1 distance, centroid 2 distance, 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 and distance. Which one is the smallest? So this is definitely C1. Which one is the smallest? This is C1, C2, C1, and C2. This is how you calculate the Euclidean distance, by the way. The Euclidean distance is just this norm of the difference. So here we have our clustering assignment, and then we have the new values of what are they called? Of C1 and C2. After we finish, we usually end up with these in a cluster and these in a cluster. So usually, or we can definitely see that this person and this person are in the same class, and these 3 people are in the other class or in the other cluster. Simply, we could say that these 2 are adults and these 2 are certainly kids or teenagers. So just a small example of what a bag of what a visual word vocabulary would look like for a group of faces like this. So we have tried to learn from thousands of images of faces of people. And here we can see these are the overall visual words vocabulary that we have learned. A lot of eyes. We can certainly see that each one of them is quite different because we did the clustering, but the eyes are always going to be there because they're pretty special for a human being. Of course, you would see different types of nose in all directions, and the rest are usually features which are not specific for, what are they called? Which are not specific for a human person. Can somebody tell me how would we remove, or somebody propose a different clustering algorithm that wouldn't suffer from this problem, right? So let's consider these as just noise in our feature extraction part. Which clustering algorithm would remove this noise?
Maybe HDB scan.
Oh, very nice, dbscan. So a noise sample is any sample that doesn't have in its minimum or its ellipse size the minimum number of neighbors or the minimum number of samples. So if a pattern is not being repeated enough times, let's say not repeating like 10 times or 20 times in every single image, then we just don't take that pattern. So here we go. We could easily build, what is it called? So this pattern, for example, this is how many times it appeared. This pattern, this is how many times it appeared. Quite very similar. We cluster them into this one. Another one, for example, this is for a person walking. So we can see the face, the hands, or the legs. This is the direction of the person walking. Yeah. Given an arbitrary image, now we are going to do this vector quantization. We can quantify and abstractly represent the image using the bag of visual words model that we have just created. Now, this one is a little bit not tricky, but not very direct, okay? So the first one would be to extract the feature vectors from the image using what exactly?
The same algorithm that we used to.
Yeah, whatever you use, right? Harris or SIFT. Step 2 would be for each extracted feature vector, compute its nearest neighbor in the dictionary created. Now, this is where the part that is a bit tricky. So previously with words, we had word, let's say yes, and we have word yes in the vocabulary. Directly, we do the mapping, right? Very easy. But now for images, we have a pattern of an eye, but we can't compare directly, right? So we can't say exactly there is an eye. So what we simply do, we try to extract some feature description of this one. We try to extract the feature description of the eye in the new image. And if the difference between these two descriptions is small enough, then we consider it a match. So this is what's happening here. We basically compute the nearest neighbor in the dictionary for each one of these feature vectors extracted from the image. Usually it's done with Euclidean distance. And then the last one would be to take the set of the nearest neighbor labels and build a histogram of length k. Length k is basically how many, what are they called? Dictionary words do we have? So now we have this histogram. Which is just a feature vector again, right? So this is 3, 4, 0, 0, 0, 0, as we described in the first part of the lecture, something like this. Now it becomes pretty easy to represent an image and do the classification, right? So you're already familiar with how to do image classification or how to do vector classification. The rest of the lecture should be pretty easy. So the image representation part is detecting interest point features, finding the closest visual word to each region around these detected points, and then we record the number of occurrences of each one, but definitely not the position of each feature point, right? So these are our code words, this is our histogram, but we don't care if this pattern existed in the left or in the right, it just exists, and this is how many times it existed in the image. So this is, for example, the 4 object classification part plus a background, so total 5 classes. So here we had different training data, so positive data, negative data. We could easily train an SVM for these images and have our model working much better. Of course, if we manage to, how do we say this? Use, instead of a weak supervision, use something for segmentation, right? And instead of extracting the features from the whole image, we only extract the features from the object itself. That would make it much, much better and give much better performances, right? So let's come back. So here we have the training images, testing images, the learning either with SVM classifier or a Gaussian kernel. And as you can see, the results are quite impressive. Of course, depending on the class, but they're still very impressive, from 98.3 till 100% accuracy. And this was done in the 2005s, right? So long time ago, considering the progress and speed of progress of computer vision, but it's still very impressive at the time. So just to summarize everything so far, we have the advantages of this bag of visual words are largely unaffected by the position and orientation of object in the image. So here we don't really care if the cat is in this place or the cat is in this place, we would still be able to classify it correctly. The second one would be, for example, if we're working on arts, pictures, for example, from Picasso or something like that, where the eye is in here, the second eye is in here, the nose is here, the mouth is here, and stuff like that. This would be unaffected by that. So it's definitely good for such cases. We also have a fixed length vector, irrepresentative of the number of sections, by controlling the number of k. Very successful in classifying images, but it still requires further testing for large changes in scale and viewpoint. So this kind of depends on whether you're using Harris or you're using SIFT. And it's pretty sensible, of course, sensitive to what feature extractor you're using. The disadvantages are very related to the advantages. So basically, we're going to repeat the advantages, but now in a bad way. So there's no explicit use of configuration of visual word positions, meaning there's no way to represent the spatial relationships of these different visual word positions. Of course, somebody would say, what if we do? And that would be amazing, right? Certainly, if we could combine this bag of visual words, and instead of making it a bag, maybe something like a graph, right? So basically, you have an eye here, you have an eye here, and you connect each one of these different components by a certain relationship, right? These relationships could be some spatial mathematical relationships. Say this one is to the right of this. And this would be a very good idea to try out and implement in general. So basically, instead of using a bag, we would use a graph, right? Pretty interesting. And the relationships between the objects in the graph would represent the spatial relationships between these patterns in real life. And the second part is that it's poor for localizing objects within an image. Why? Because it doesn't care about the position of an object in an image. So thank you very much. Now the rest of the lecture would be just like a small revision of what KNN is. And we would do like a small overall revision of everything. But so far, before we go there, does anybody have any questions? Or does anybody want to basically work on this for their final project, right? Hello? Anyone has any questions? Nope. Oh, very smart suits. Or probably my internet is bad. One of these two. Yeah. Now for KNN, the K nearest neighbor classifiers. Simply what we would do is we have a data set here. This is our training data. And we get a new sample like this. And we try to find what are the closest objects to this one from our data set. So the basic idea is like, if it walks like a duck, quacks like a duck, then it's probably a duck, right? So objects of the same class tend to repeat the same patterns or tend to do the same things or look the same. So the learning task is given a set of, well, let's say samples and their classes. Do nothing. That's why it's called lazy learners. So basically, instead of building some sort of a model, like, let me just check You guys sent an image. Somebody did send. Is it okay to merge? Ah, okay, so it's Karam, right? Till the end of the course. Okay, this is Karam. Yeah, so yeah, instead of building some sort of a representation of the model using a linear model like SVM or let's say, or some sort of linear, what is it called? Linear regression or logistic regression function. Now we're just going to save the data as it is. We're not going to do anything, and that's why it's called a lazy learn. So the learning part is exactly O of 0, right? We don't do anything. Now the classification task is very intensive or like requires a lot of time. Given an instance XQ that we want to classify, find the training set instances XY that are most similar to XQ. And then we return the class of yi, or the class of the average of the pixel of the samples that we took. For example, we come here. In this case, everybody can see that in its neighborhood, we have more negative samples than positive. Hence, we will classify this sample as a negative sample. Distance matrices that we could use are the following. So there's the Euclidean distance, pretty good, but after a certain number of features, Euclidean distance tends to break down and doesn't give good performances. There is the cosine distance, and this is pretty nice, especially for bags of visual words. It works pretty well because it works mainly on the orientation. And then there is the chi-squared. So this one works pretty well also with distributions and stuff. But this one I think is certainly the best in my opinion for larger number of features. Yeah. As we can see, nearest neighbor classifier is pretty competitive. This is for the MNIST digit recognition dataset. It was able to give a test error of basically 5% or an accuracy of 95%. For a machine learning model, this is certainly very impressive. And that's it for our lecture. Does anybody want to stay or stick around and discuss basically their project or discuss some ideas that they would like to implement for those who are aiming for implementing a new paper or some new idea? Please stick around and feel free.
Could I discuss my project and
Yeah,
ask
of course,
if
go
it's
ahead.
like for complexity? I want to implement something like YOLO-based sign language detection and recognition. First of
Really
all,
basic.
is it even possible, and how complicated is it?
We can do it in half an hour right now, or like 3 minutes. Let's.
Really? I
Yeah.
mean, it's not a difficult project.
Yeah, you can already watch
RoboBlocks.
Convene and Networks. They already implemented several of these.
No, not RoboBlocks.
So it doesn't make sense to implement it as a project.
Sign. Yeah, it would make sense. Why not?
Okay, but as you said, it looks like very easy.
Let me show you how easy it is.
You could implement it like on, there are different types of sign language. And as I understand, most of them are trained on only one sign language. You can make it like for different.
Huh? One, two, three, four, five, six. Let me check just to make sure that we are working with. No. No, sorry. Done. finished your project. So as you can see, it's as simple as that. You go to the dataset here in RoboFlow, especially for the dataset that you chose. It's pretty easy. You come here, select the model that you would like, or select the dataset version that you would like to use. There we go. Here it gives you the code to basically download this dataset, copy the code, press choose the model, choose whatever model that you want, go to its Colab representation, and simply just change, what is it called? Change here the dataset source. The rest of the code would work pretty well for it, right? So here it's being used to detect different blood cells. The second that you change the dataset, it's going to read the names of the classes, the number of classes, read the images of this dataset, and basically repeat the training process, but for this task in itself, and the task is finished. So as you could see, I would say it took less than 2 minutes overall. So it's a pretty easy homework, but still it is a homework, and that would you could increase the difficulty level by doing some sort of evaluation of each one of these models, right? So comparison, let's say. So instead of training, for example, YOLO v5 on PyTorch only, you train scaled YOLO v5 or CSP, and then you train, for example, YOLO v4 tiny and YOLO v4 M, YOLO v4 with mesh, or YOLO v4 with something else. Like there are different activation functions, there are different scales, there are different versions of YOLO v4. And then of course, there are different versions of YOLO v5. So there is YOLO v5S, M, L, X, and stuff like that. The rest are pretty useless. Yeah, here the rest are pretty useless. Of course, you could use PP-YOLO. It's pretty good too. And then you could compare each one of these based on mean average precision and or based on the time of training and time of inference, and build a report about these. Actually, it could be even a paper about all of this, right? Just like a comparison of these different algorithms in terms of speed, accuracy, and there you go. You have it. Like it takes less than, let's say, 20 minutes to be generous to finish the coding of all of these algorithms, because you have nothing to do, as I said, just change the name or the source of the code of downloading the data, and the models that are given to you by RoboFlow will do the job or will do the trick on their own.
So you suggest to make it a bit more theoretical?
One would say a bit more theoretical, but someone else would say it's pretty useful. Why? Because if you're going to be working in a company, they're not going to really care if you're going to implement YOLO v4 from scratch. They will certainly care if you're going to be able to basically build or train YOLO v4 pretty efficiently and very fast. That's all they care about.
Okay.
Yeah,
Thanks.
so it's definitely very theoretical, and it has a lot of practical experience that would give you what an industry would want. But a good project overall, yeah, certainly. Anyone else has some ideas?
Yeah, I wanted to ask if my project is suitable. So the idea is to build trajectories for self-driving cars using LiDAR data, which are 3D points, and camera data. So on the input, I have LiDAR point clouds and images from front view, and on the output, I generate trajectory which my car needs to follow.
Good. So basically, you're trying to do lane detection or something like that?
Yeah, the idea is to leave it to neural networks. So basically, I can do it manually, detect lanes, find center line, and etc., etc. But
yeah,
at the same time, I can insert reference trajectories from human beings and propose to neural network to guess how to drive in arbitrary environment.
That's a very good, very good idea. I would like to see that. I think in every single one of the courses I taught, every person, at least like 2 groups would do this exact idea. So go ahead for it. It's pretty nice.
But they did the steering probably and throttle commands.
I'm not really sure. I just always forget these things.
Like usually people do like NVIDIA did in 2015, and they output steering and throttle commands. But this is very limited to all possible scenarios. That's why my proposal is not to output steering and throttle, but output the trajectory itself.
And how would you represent the trajectory?
Well, so it is a sequence of 3D points, so we can fix output tensor, for example. Model will always output 100 points, which consist of 3 XYZ coordinates and probably time associated with it. I can also fix it, so probably 100 points with discretization of 0.1 second, for example. And model will regress XYZ.
Okay, got you. Certainly, it's pretty interesting. I would like to see different benchmarks also. You know what benchmarks are?
For that, there are no like a public benchmark. I know like about 1, 2, 3, 4 data sets that are not for this problem exactly, but I can use them as a benchmark. So I have all bounding boxes of objects and a human proposed trajectory. So I can, for example, compare L2 distance between the generated trajectory and taken trajectory.
Usually when we say the word benchmark, we don't really mean on a different data set, but we mean on the same data set, but a different model, right? So I want
exactly
your same data set, but with different ideas. So you just said you will be working with a fixed length output. I would want to see something with not a fixed length output, right? So what would something recurrent based on RNNs would look like?
Well, yeah, that's possible also.
Right. So try to experiment with different basic idea. This is what benchmarks are. So just the basic implementation of this method using something very simple, right? Let's say some of the methods that you have seen in this course, some of the direct methods that you have seen in this course, maybe some of the, help me out. I forgot what I was going to say. Yeah, some basic neural networks that are very direct for this method. And let's say some KNN or something like that. Something pretty basic.
Okay.
Yeah. Okay.
I'm not sure about the benchmark because there are no like public datasets exactly for this purpose. I like searched a lot.
No, for your dataset. You have a dataset, right?
I can collect it in simulator, for example. And I wanted to use 4 public datasets that are available on the internet.
Okay, so just combine these 4. And for each one, like for this combination, solve the problem using your method, and then solve the problem using other simpler methods. These simpler methods should not require any thinking, right? So these simpler methods should be very basic ideas. This is just to explain or give a certain comparison between your idea and other ideas which are simpler, and definitely why is your idea worth it and why is your idea much better than the others.
Okay,
this is always very important for like for a domain or for a new idea in a new data set, and certainly in a field that wasn't already explored. So if you just give your results like this, people are not going to be able to evaluate it very well. They're not going to be able, okay, so 80%. What does 80% mean? Is 80% good enough or is it too bad? We don't know. But if you give your result 80% compared to other models, 30%, okay, now people will see, oh, 80% is pretty impressive. You see?
Okay.
Yeah, so adding these benchmarks will certainly allow you to publish your work in a much better journal or conference.
So could I also ask a question
Yeah,
about
of course.
the
Go ahead.
project? I researched the list of topics that you published and the question regarding other projects, and I'm kind of confused and embarrassed because I proposed you on the first lection that I want to do something with style transfer. As I remember, we will not cover this on our course, and maybe I want to do some modifications of this, maybe style transfer from two images at the same time.
Okay.
And is it a legible project? Maybe I could wrap it like on the Flask or something like a Telegram board. Will it be okay? It will not be publishable as other work, but it's like still practical project. Is it okay to?
Oh, you would be surprised how interesting the style transfer problem is. Like during the last course, or like the advanced computer vision course, the most important or most interesting project I had was something working on style transfer. And it was a very big project, and they are now building startup using this style transfer project. So definitely there is a lot of potential there, and you're going to find
was
a
it
lot.
Like something style gun or something?
It was a bit of an improvement over like the basic style transfer one. So there is I forgot the names, but there was like version 2 and stuff like that. Yeah.
Okay. If I implement it from scratch by myself,
useless. For me, I don't like from scratch implementations.
Okay, not from scratch, but it will be still quite old paper. Is it okay? Because it's not something fresh like other guys doing.
Preferably, if you are really interested in style transfer, there is a lot of like new applications of it. There are new improvements of style transfer. So instead of going like the previous way of changing the pixel values based on like gradient descent and trying to find the style and the content, what are they called, losses, and improving them, you really shouldn't be doing just that. Try to go for something a bit more advanced or a bit more recent, right? And the implementations are all out there, so there's nothing really to fear. It's just going to be a bit of reading and a bit of experimenting.
But honestly, I did not hear about something new in classical style transfer. Style guns, yes, but not something as simple as style transfer.
So just like small Googling, it should work. Style transfer. So for me, this was like the first thing that you could find for style transfer. This is like the first link on Google, and boom, there you have lots of new papers on ICV, ACL. So this is like 2015, 2017. Yeah, definitely something. CVPR 2021. So you know, if it's here in CVPR 2021, there's nothing better than this one. Yeah, so go ahead, experiment with these ideas. Let me just send you this link so that you don't miss it. And this is like the first thing you would find on Google once you type style transfer, right? So it's not like something that requires a lot of search. It should be quite easy to find all of these different applications. Anyone else, for example, interested in working on something new, maybe experimenting with some new ideas?
So the most easiest one, like the fastest, is to train some new classifier or detector. It will be enough.
For me, training a classifier would definitely be too easy, right? So at least go for training an object detector, right? Or a set of object detectors. Yeah.
Okay, thanks.
That's nice. Anyone else has any questions? maybe someone was interested in the idea of bag of visual words represented like with added spatial features. Nobody was interested in that idea. Nice. Well, if you guys don't have any other questions, we could easily like finish the lecture right now. And for those who are like a bit too shy, you could always text me and I would discuss with you guys your ideas. So thanks a lot. Have a great week and see you on 2 days.